Hello, everyone. Welcome. So today we're very happy to have Edray Goins, who will tell us about clocks, parking garages, and the solvability of the Quintic, a friendly introduction to monodromy. And how would you like the students to ask questions?
They can either put it in the chat or they can raise their hand here in the window. Either one is perfectly fine. We'll try to get to them as we see them.
Okay, sounds good. So go ahead.
All right. Yeah. Well, thanks very much for this opportunity to give a presentation here. I know that there's going to be a lot of information here in the slides. So if any of you would like a copy of the slides, I'm going to give them to Simon afterwards. So just feel free to let me know. But hopefully this will be a fun little story here. Let me first start off by saying that there are plenty of opportunities in the math community to get involved in doing research, especially on the kind of topics that I'm going to say here today. I myself run my own REU. I'll call it Prime, the Pomona Research and Mathematics Experience. We typically like to take students that have never done an REU before. So that is students that have either finished their first year of college or finished their second year of college. We have not run the RU the last 2 summers. We don't really plan to run for next summer, although we are going to apply for NSF funding. Many of you have probably heard NSF funding is a little bit weird these days. So we're hoping that we'll run summer 2026. We're just not quite sure how all of this is going to go. But either way, I would definitely say take a look at the website that you see here, research.pomona.edu/prime, and that'll give you an idea of whether we're going to run for this coming summer. But I want to say that some of what I'm going to talk about today is actually based on work that I did at a different RU. There is a research institute there in the Berkeley area. It's actually run by UC Berkeley called SL Math, the Simon Sloffer Mathematical Sciences Research Institute. They are formerly known as MSRI, the Mathematical Sciences Research Institute, and they run a wonderful undergraduate program there called MSRI UP. About 5 years ago, I had a chance to work with 18 great undergraduates, and they helped to put together a lot of the graphics that you're going to see here today. So here's another opportunity if you are interested once you go off to college for doing research. I've done MSRI up a couple of times now, and I really do enjoy working in that program. Now, these are two programs for undergraduates, and there also is a way that you can keep up with this kind of research if you're a faculty member. So you probably have heard of RUs. This is Research Experiences for Undergraduates. There is a program out there for undergraduate faculty that's called REUF. So I know that this will be down the line for a lot of you, but I wanted to point out that almost everything I'm going to say today is based on work that I did with a group of faculty members back about 10 years ago. I also worked with a similar group of faculty, the same program, last week at a research institute in Providence, Rhode Island. So some of what I'm going to say here today is fresh off the press. We just finished writing it up last Friday, and we're planning to submit this for publication sometime soon. So let's jump into the math here. I want to start with this idea of a clock. Now you can see here with this clock that I have these three hands that are spinning around. I have the second hand, that's what's moving around the fastest, the minute hand, that's kind of the middle speed, and then the hour hand, that's the shortest and that's the slowest. What I want to do here in this talk is kind of think about these three hands and how they're spinning around, but more importantly, I want to think about the relative speed of each of these, right? So again, I have the second hand, the minute hand, and the hour hand. Now, mathematically, we can write down the hands of the clock using formulas like what you see here on the screen. So let's maybe kind of normalize everything so that the hands of the clock are just going to be sort of specified by this 1 point f of t, or I should say here this L tilde of t, of radius 1. And the n that you see here is going to tell me the speed by which everything moves around. So let's just kind of normalize by saying when n is equal to 1, this will be the minute hand. And now if I think about it, I have the numbers 1 through 12 that are on the clock. So every time the minute hand goes all the way around 1 revolution, 60 minutes, the hour hand is only going to go 1/12 of the way. So if I let n to be 1 for the minute hand, then I want n to be 1/12 for the hour hand. Now, every time the minute hand goes all the way around once, remember that 1 minute also consists of 60 seconds. So that hand that was moving around really fast should now go around 60 times because I have now, say, 60 seconds that are in 1 minute. So I can kind of keep track of the relative speeds by looking at this number n. Sometimes n here will be an integer, like n is 1 or n is 60, or n might be a fraction, something like 1/12. So let's try to write all of this in a slightly different way. I want to use here Euler's identity, which says that if maybe I write x is sine and y is cosine, then this complex number, x plus iy, I can write using this idea of e to the I theta. Right? You might remember this formula, the e to the I theta somehow involves cosine theta plus I sine theta. So if I play around with this just a little bit in just the right way, then I can write this function you see here at the top of the screen as a composition of two functions. First, I have this function w of z, which is some complex number times z to the n. The I here just says that when t is equal to 0, I need to be pointing straight up, right? That's kind of high noon there on the clock. And then the z to the n, remember that n keeps track of the speed. So either n is 1 if I have the minute hand, or n is 60 if I have the second hand, or n is a fraction 1/12 if I have the hour hand. And the L of t just tells me the fact that I'm looping around this clock. Notice that here I've kind of written my L of t so that it's a clockwise loop, right? Just moving around the way that I would on a clock. So kind of using all of this, here's the takeaway I want you to think about. Let's just ignore the loop for the moment because the loop doesn't really tell us much about what's happening here. What really is important is how things are working here with z goes to z to the n. Right, so remember that if I take n is equal to 1, that's just going to be the minute hand, but I care about these other two numbers. If n is 60, for every one rotation of the minute hand, I have 60 rotations of the second hand. And if I consider n to be 1/12, that just says for every one rotation of the minute hand, the hour hand only goes 1/12 of the way. So I want to keep track of this idea that if I have a fractional exponent, I maybe don't have a complete loop. I'm only going to go part of the way. This idea here is what's going to motivate the rest of this presentation. So this is just one example of looking at the three hands on the clock, but I want to try to ask, are there other examples of what's happening here? Well, some of this is motivated by what we see in a parking garage. Right, so here in California, we spend a lot of time going around parking garages, and kind of the idea is that you have this structure, maybe it's three-dimensional in shape, but whenever you drive into a parking structure, you're going to spend time maybe like on the first level, driving around trying to find a car. If you don't find one, then you would loop around to the second level. There on the second level, you drive around trying to find a place to park. If you don't find anything, you loop around to the third level, and that's sort of what you see here in this diagram. On each level, level 1, level 2, level 3, you're going to be looking for a place to park, but then it's this ramp here that allows you to kind of go from one level to the next level, right? It's sort of like saying at each level, levels 1, 2, and 3, it kind of looks the same, but then I have a way to really come to walk up going from one to the next, but kind of rising up in the levels here. It really isn't a flat two-dimensional structure. It really is a spiraling kind of a three-dimensional structure. Well, we as mathematicians like to kind of generalize this. So you might think of that parking garage kind of in this abstract kind of drawing here. Notice that it's the same basic idea, that maybe I'm going to walk along the ramps and then I'll kind of go from level 1 to level 2 to level 3. Everything locally kind of looks like it's flat. It's about the same, but I'm still able to kind of spiral up and then kind of walk up these different levels. So this here really kind of gets at a more general concept. You can see here on the right-hand side that I really want to think of my parking garage as kind of these ramps that I'm kind of winding up to go from one level to the next to the next. The fact that I can really project everything down to just looking like a circle is the same as saying, what if I were at the top of the garage, maybe even in a drone, staring downwards? Well, every level of the garage looks the same. it looks like it's nice and flat. And if I had a drone that could maybe kind of see through the concrete, it would just see a car as it's kind of going up from level 1 to level 2 to level 3, almost like it's just driving around in a circle. It would seem that the car really isn't doing anything interesting at all. And that's sort of the idea of the picture that you see over here on the right. Everything kind of looks the same if I were to flatten it down. Right. See that there's a quick question here. Was that the Riemann surface of natural log of z? Yes, it was. I'm going to come back and say a little bit more about what I mean by Riemann surface, but if you've already seen some of this before, that's exactly right. So one question you can ask is, why do people believe the Earth is flat? Well, as I just mentioned with the parking garage, if I'm at level 1, or if I'm at level 2, or if I'm at level 3, everything looks the same. It looks like everything is a nice flat surface. It's just that one place where maybe I have to kind of ramp up going from level 1 to level 2 to level 3, that spiral. But otherwise, if I kind of ignore the spiraling, everything looks flat, everything looks Euclidean. So you can really say this is why people get lost in parking garages so easily. It's because everything on the parking garage, all of level 1 looks the same as level 2, looks the same as level 3. But what I really want to say, putting all this together, kind of using the picture on the upper right, is that the parking garage is an example of a covering space, right? It's going to allow me to say that I really have these loops, but I want somehow to kind of stretch out these loops into 3 dimensions. I'm not going to worry about a lot of these very technical terms today, like Euclidean and covering space, but I want to kind of give you an idea of what the definition should be based on the ideas that we're going to talk about today. So I want to try to think a little bit more about like this parking garage idea. This leads into the concept of a Riemann surface. Now, Riemann surface should be very naturally what you expect. We have things like this sphere here. We have things like, say, this torus, if you will, this anchor ring. More generally, I can use phrases like a compact connected Riemann surface to draw things like this green object that you see here at the bottom. The way that all of these are related is that they are all compact, right? So I can literally hold them in my hands. They are connected, so I don't really have them kind of broken up into different pieces. I have 3 pieces here on the screen, but I can take each piece individually. And the Riemann surface idea says that I have here a surface, and I want to keep track of how many holes I have. You see that the green object here at the bottom has 3 holes, so I would say that it has genus 3. The one on the upper right, that torus, only has 1 hole. I would say that has genus 1. And the one on the upper left is a sphere. That doesn't have any holes. I would say that that has genus 0. For everything that I want to say today, I'm only going to focus on the sphere, what's happening on the upper left, although there are ways you can generalize a lot of what I'm going to say here for any one of these compact Riemann surfaces. So let me spend a little bit of time thinking a little bit more, what is this sphere? What are different ways in which I can think of this? Well, one definition I'll write down is this idea of the projective complex line. So P1 of C just means I'm going to take the complex numbers and I'm going to add in one more point. When I'm going to call infinity, I'll say that I'm not really specifying what I mean by positive infinity versus negative infinity. I'm just going to say infinity, and I'll try to make a little bit more sense of that in just a moment. Another object I can write down is this S2 of R. So this would just be the set of real points in 3-dimensional space, such that I have this condition, the sum of the squares is equal to 1. I claim that these two are the same, right? This P1 of C and this S2 of R. And eventually I'm going to use this to try to draw graphs on the sphere without crossings. Let me come back to that later. But why are these two objects the same, P1 of C and S2 of R? There are 2 different ways you can see this. One is just by using algebra. Let me write down an explicit mathematical, or if you will, algebraic expression. If you give me a complex number W, I can write down this point in 3 dimensions, x, y, z. Notice that I can write x, y, z in terms of the real parts, the imaginary parts, and then the length of W. Going in the opposite direction, if you give me a real point x, y, z, satisfying x squared plus y squared plus z squared is 1, I can write down this complex number w. And let me point out here that using this algebraic expression, I can identify 0 as a complex number with the south pole, 1 as a complex number with the point on the equator, and infinity as an extended complex number with the North Pole. Now, there's a comment here in the chat window that they are the same due to stereographic projection. That is absolutely right. The picture here is supposed to give you a geometric way of seeing why these two here are the same. The way this picture works is as follows. Let's say that you give me a complex number w. I want to think of the complex numbers as the set of points in this gray plane here. That gray plane, if you will, is like the set of complex numbers. So I have a black dot, that's my w in that gray plane. Let's draw a line to the North Pole of that yellowish object, that is my S2 of R, and that will intersect at this red dot. That red dot I'm denoting as XYZ. It is a real point on the sphere. Conversely, say that you give me a red dot here on the sphere. This is this point XYZ. I can draw that through the North Pole, and then that should intersect the gray plane here with this black dot that I'm calling the complex number W. So now you see that there are two different ways you can think of this. One is algebraically by writing down these formulas. Another one is geometrically by using this idea of stereographic projection. But this is why I say that the projective complex line is the same as the Riemann sphere. This here is our example of a Riemann surface, very specifically a compact connected Riemann surface. But again, let's not worry about all of those adjectives. So why don't we go back to where we were before? Remember that we were talking about the hands on a clock, we were talking about loops, somehow we got sidetracked, started to talk about Riemann surfaces. So I want to go back to this question of what does one mean by these paths and by these loops? So I want to kind of pause for a moment and think a little bit behind what are these loops? What do I mean by that? Let me consider loops maybe that kind of live on the sphere that start and end at a given point. So just fix your favorite point on the sphere and let's take a look at all of these loops. So I'm going to think of that in terms of these pictures that you see here. So here I have the sphere, and this is kind of a movie going from left to right where I'm taking a loop on the sphere. This may be at that blue dot you can see, that's my Z naught. And now what I'm going to do is think of this black band, that's my loop, is like a rubber band, maybe around something like a bowling ball. I can take this rubber band and I can kind of slide it off to the side, and you'll see that there's really nothing to kind of stop this rubber band from sliding, and this rubber band will eventually slide off to one side. It'll kind of contract down very small, and then it'll just fall off the sphere. Mathematically, I'm saying that my loops up to homotopic equivalence, that just means that I'm allowing myself to kind of slide along the surface of the sphere, will just be trivial. They can always contract down to a single point. So what I would say is that this fundamental group is trivial. The idea of the fundamental group is that just here I have loops, and I care about loops where I'm allowing myself to kind of contract and move around and what have you. So the sphere itself isn't really that interesting because there really aren't any interesting loops. Any loop that I have, any rubber band, can just contract down to a point. But what if I start to puncture away at places here on the sphere? So let's take the sphere and let's maybe cut out a small circle. We can maybe cut out a small disk near the North Pole, and let's do the same thing. Let's ask about loops. Well, if I have any loop, I don't have to worry about trying to maybe slide the rubber band up towards the North Pole, because at that point, I can't really contract anymore. I'm not allowing myself to go past that disk that I cut out. But let me go in the other way. Let me slide it down towards the bottom, towards the South Pole, and the same thing as before is going to happen. That rubber band, as I slide it down to the South Pole, will eventually kind of contract to the point and then just fall off. So I get the same idea. The sphere minus one point has a trivial fundamental group, right? There's really no loops that are interesting if I have that. So let's go for broke. what if we talked about the sphere minus 2 points? So now I'm going to cut out a little disk at the North Pole and cut out a little disk at the South Pole, and then ask about these loops. Well, I claim that there's a one-to-one correspondence from the loops to the integers. Well, one way to see this is if I have my sphere, now I've kind of cut out a little disk at the top, cut out a little disk at the bottom, and if I kind of flatten things a little bit, I actually have a cylinder. And if I have a cylinder, now let me kind of look down the cylinder. So here I'm at the top, kind of staring down, and I can see from my loops on the left-hand side how many times I'm kind of winding around my cylinder. So maybe I'm going to wind around so many times clockwise. I might wind around so many times counterclockwise. But the point is, I can't really slide my rubber band off because, again, I've kind of cut out the disc at the top, cut out the disc at the bottom. I'm now not allowing myself to move past where I cut out. So you can see here on the left that winding around 0 and infinity, that is, remember my cylinder, so I'm kind of winding around this way, winding around the other way, really does depend upon the number of times I'm either winding around clockwise or counterclockwise. So I might say something like a negative integer corresponds to the number of times I wound around clockwise, whereas a positive integer tells me the number of times I wind around going counterclockwise, right, in the opposite direction. Remember that this here is a cylinder, so the picture on the right goes back to my idea there of a parking garage, where I can really see there on the cylinder that I'm kind of winding around, but then as I can kind of slide my loop up and down, eventually I can just flatten it out. That's the picture on the left now, and just ask, well, how many times did it wind around clockwise? How many times did it wind around counterclockwise? So this here is what's called a winding number. And literally the integer here just tells you the number of times you wind around counterclockwise or that you wind around counterclockwise. Right, so that's the question in the chat window. Loops with differing winding numbers are not homotopic. Yes, they correspond to different homotopy classes. So the idea is that the homotopy class, the equivalence class, is uniquely determined by its winding number. How many times are wound around clockwise? How many times are wound around counterclockwise? So in this case, the fundamental group is the integers. It's no longer trivial like the other two, but in this case, it's something interesting. It's non-trivial. So now we have the sphere minus no points. That's a trivial group. Sphere minus 1 point. That's a trivial group. Sphere minus 2 points. We get back the winding number, so it's just the integers. So why don't we do the sphere minus 3 points, just to see what happens here. Before we do that, let me kind of think a little bit, is there another way to think about those integers that we talked about before? So I want to go back to how we began everything with this function, right? Z goes to Z to the n, and kind of what's happening there. Well, let's say that we have the twice punctured sphere. Remember, this is the cylinder. I'm going to cut away the North Pole, cut away the South Pole. I want to ask now about a loop that starts and ends at Z0. Remember, we just said that all of our loops are in correspondence with the integers. So if you give me any integer k, I'm going to think of that as this loop here, L of t. Right, so the k here is the winding number. It's exactly what you expect. I start at Z0, and I just wind around k times. K can be positive, negative, or 0. Let's ask about what happens if I take this function wz, which is a constant times the power of z, and if I compose. So now what I'm going to try to do is take that function L of t, and let's ask what happens if I take the nth root. Remember how we said earlier with the clocks, things like, with the minute hand, the second hand, the hour hand, that every time the minute hand goes all the way around once, the hour hand does not go all the way. It only goes 1/12 of the way. So I want to try to do the same idea here. I want to ask, as I loop around this L of t, what happens to the w? Well, the claim is there's some constant a so that my W, if I go all the way around once for L, it doesn't quite go all the way. So that is W of L of t may not equal to W of L of t, but it might be some number times W of L of t. So I'm going to try to understand that a little bit more. Well, the way you can work this out is just by staring at the composition. So again, L of t is a constant times some power e to the 2 pi I kt. Remember Euler's formula. So now let's try to do something like take the nth root, and something weird happens because I don't quite get back to where I started from. I might have to have some kth power of a primitive nth root of unity. Right, literally just kind of plug in the formulas and see what happens here. The way to think of this geometrically is, remember what we said earlier about the minute hand and the hour hand. In that case, n would be 12 because I'm taking the 12th root. Maybe k is equal to 1. So as my minute hand goes all the way around once, my hour hand, according to what's here on the screen, will pick up a 12th root of unity. I'm not going all the way. I'm only going 1/12 of the way. That's exactly what's happening here much more generally. If I have my L of t, which is a complete loop, my W of L of t says I'm not going to have a complete loop. I'm going to have a partial path. And the path here just says that this number A says I'm only going to go part of the way, not quite all of the way. Another thing to take away from this is, if you give me this loop L, I can associate that with an integer k, but then I can associate that with some root of unity, some non-zero complex number. So let's just put all of that together into one big map. So again, sorry, there's a typo here. This gamma should be L. If you give me a loop L, I can associate that to its winding number k. And now, according to what we just said here, this W function says I can really associate that integer k to a kth power of a primitive nth root of unity. So while the fundamental group, this pi1, is the same as the integers, I can kind of represent this by nth roots of unity, right? Give me an L, I can write down this number A, which is some kth power of an nth root of unity. This is what we call a monodromy representation. Notice that I had to fix the function W, and once I fix W, then I can say that this complex number A has to come about. So more generally, this is what we want to try to do. If you give me some surface X, I want to try to take a look at this pi1, and then there should be some function W that allows me to kind of really think of the elements here as complex numbers or something like this. So we're going to come back to this and talk about this in some detail. Now, just to kind of get a flavor of where things get weird, that was the sphere minus 2 points. Remember, that was the cylinder. We can try to ask about the sphere minus 3 points. So let's take away, doesn't matter which 3 points, 0, 1, and infinity. It really doesn't matter at all. Well, the statement is this group, this fundamental group, is a really nasty group. It's what's called a free group, and it's a free group on 2 generators. I don't want to try to go over what all of that means, but this is going to be kind of the big question as we're putting all of this together. We know what happens with the sphere minus no points, minus 1 point, minus 2 point. We know for the sphere minus 2 points, we can write down the so-called monodromy representation, but the sphere minus 3 points gets weird. So what I really want to know for the rest of the presentation here is, why would we care to study this group? So I've tried to give you kind of the bigger picture to say that there's this weird idea of fundamental groups and loops and what have you. But what I want to do is kind of shift gears and really get into this question of, why are we even caring to do this? Why are we even writing down any of these definitions? Right, there's a really excellent question here in the chat window. What about the sphere minus n points? What do we know for the groups in that? So it turns out that these are all related to the free groups on R generators. So in this case, my R will be n minus 1, right? So if I take away 3 points, it's the free group on 2 generators. If I take away 4 points, it's the free group on 3 generators. It's really just going to be n minus 1. It won't be 2n plus 1. So these groups get really nasty. There's another theorem that says that the free group on any number of generators can be embedded in the free group on 2 generators. And that's not an obvious theorem. So yes, it says if I take the free group on 5 generators, maybe what I get by the sphere minus 6 points, that is a subgroup still of the free group of 2 generators. And again, that's not meant to be obvious at all. So if you're wondering, to kind of answer the question here in the chat window, what happens if I have the sphere minus so many points? I can think of that as being subsumed in the question of what happens if I have the free group of 2 generators, that is the sphere minus 3 points. It's a really weird thing, but this is why this group is a really nasty, non-intuitive group. But that really is an excellent question. All right. So why do we really care to study such a group? What's actually happening? We have all these funny definitions, but can we take a step back and ask, what's the motivation here? I want to shift gears and go back to some relatively elementary math that actually leads into some interesting, deeper mathematical ideas. So hopefully you all remember that the quadratic polynomial has a formula that you can find its roots. So if I wanted to find the roots of this quadratic polynomial here, then I can find the roots by the so-called quadratic formula. I want to think of this in a slightly different way that's going to help me a little bit later. I observe that I can express these two roots in terms of the function here I'm writing as w of z. So notice here, I'm just kind of playing around a little bit to say that if I have this quadratic formula, then I can really write everything in terms of the square root of something. But that square root, I want to think of as, like, if you will, the inverse of this function z of w, which is w squared. Right? So it looks like it kind of, at first sight, I'm not really writing anything interesting here. But again, I'm just simply saying that I can express the quadratic formula as the inverse of a certain function, right? This wz is equal to z squared. So let's just ask a silly question. What do we really mean by the square root of something? Now, if you think about it, square root really isn't a well-defined concept, because if I ask you, well, what's the square root of 4? Well, there's really 2 answers. There's a +2 and a -2. So when I really write the square root, that really isn't a well-defined function, so I have to be a little bit careful there. So let me give you a rigorous definition if I wanted to take something like the nth root of a complex number. Right, and there's a good question here. Isn't square root symbol only defined by the positives, though? Notice I never said that I'm taking the square root of a real number. I'm actually taking the square root of complex numbers. And now it gets weird. So for example, what if I wanted to take the square root of 1 plus I? That's no longer a real number, so I can't say like the positive square root, because what does it mean to take the positive square root of a complex number? But that really is a good question. So more generally, if you give me a positive integer, not just n is equal to 2, but any positive integer you want, then I can say that this function z of w, which is w to the n, has an inverse that looks like this power series expansion. So here I'm going to just take a look at z to the 1 over n. I can look at the Taylor series expansion of z to the 1 over n. I don't really want the Taylor series around z is equal to 0. I want the Taylor series around z is equal to 1. So once I do that, you see the infinite expression here at the bottom of the screen. And so I can write this expression using some fancy notation here, 2f1. I'm going to come back and talk about what I mean by 2f1, but this is just to say for the moment, I can express the nth root of a number using this weird Taylor series expansion. So this will be my rigorous definition of taking the nth root of a complex number. It's just this infinite series expansion here. All right, you're probably thinking, so what? I'm just kind of writing this in a funny way. Well, let me think of it now in the following theorem. Remember I mentioned earlier that I was doing research with faculty members about 10 years ago. So here's where I want to try to get into exactly what we did 10 years ago. So again, let me just kind of recap what I just did on the previous slide. I want to consider a quadratic polynomial. I know that I can express all of its roots in terms of this w of z here. Remember this, morally, this w of z is like the square root of z, but I'm going to write it out here as this infinite Taylor series expansion. And then at the end of the day, we're going to evaluate this at this number z naught, right? That's all that we're going to do. So according to that previous slide, that's straightforward. It's a slightly weird way to write the quadratic formula, but it's valid nonetheless. Right, and there's a question here, isn't that the hypergeometric series? Yes, it actually is. And that's going to be exactly where we're going to go for the rest of this presentation. But I'll get back to that and I'll say what I mean by hypergeometric series. Now that we have these formulas, let me think of the following idea. Remember before we kept talking about these loops. Let's go back to a loop passing through some number z0. So now I'm going to take this loop, right, just this loop around 0 maybe, and let's plug back in for w and ask, what does that say for the composition, this L tilde? Notice that my L tilde, I really have two possibilities because I have a plus or minus square root, and I want to stare at these two formulas here. Well, when t is equal to 0, remember that I'm starting with L of 0 being z naught. And so then my L tilde is just going to correspond to my x1 and x2. On the other hand, if I plug in t is equal to 1, remember I'm going to go all the way around for my path one time. But when I take the square root, right, n is equal to 2, I'm only going to go halfway. So now I see that my L tilde, when t is equal to 1, the signs get flipped. And it's no longer x1 and x2, it's actually x2 and x1. Everything gets interchanged. What I want to do is show you a movie that should really emphasize what's happening here as I plug in any general loop L of t. So here on the screen, I'm going to show you kind of two pictures. There's what's on the left and what's on the right. On the left, I have my two roots, x1 and x2, but really I mean L tilde 1, L tilde 2. Those will be my two paths. On the right, I will have my loop L of t, and the two red dots just correspond to 0 and 1, right? So I'm just looping around 0, looping around 1. And now you'll see that as I move my cursor on the right, remember that's my L of t, those are my loops. Notice how the two roots on the left start to move around, right? So again, on the right, I have my L of t, that's my path. I can do a path around 0, a loop around 1. I can do my loops however I want. That was the whole idea of the fundamental group, right? Just have any loop that I want on the right-hand side. On the left-hand side, that's my L tildes. Those will be my paths. And now you can really see how those two get swapped around. This is the idea of monodromy. As I'm looping around on the right, those are my loops, I get these weird paths for the two on the left. In fact, you can really see, the only interesting thing is when the two on the left just kind of swap, right? The x1 and x2, because everything else is just going to be homotopically equivalent, just saying that I just have those two, right? The swaps. So that's what happens for quadratic polynomials. So what about cubic polynomials? So if you haven't seen this before, there are these really interesting formulas that tell you that if you have a cubic polynomial, there's something called Lagrange's method that allows you to compute the three roots of a cubic polynomial. I'll just kind of quickly say how it goes here. You know, with the quadratic formula, you kind of say that it's like something plus the square root of something. Lagrange's method says make the assumption that your roots are in the form something plus the cube root of something plus the cube root of something else. You then play around with it, you get back what's called a resolvent quadratic. You then use the quadratic formula. Those allow you to figure out the D1 and D2, and I can express all of this in terms of the discriminant of this cubic polynomial. So the point is, I can write explicit formulas that allow me to write down the roots of any degree 3 polynomial, right? And in fact, there's these really beautiful theorems that say that back in the 1500s or so, there were these three Italians, De Ferro, Cardano, and Tartaglia, that tried to work to figure out what are the roots of a cubic polynomial. But what I want you to take away from this is, the statement is, the roots of any cubic can be expressed using just square roots and cube roots, right? That's all that it says. You can write the roots of any cubic using square roots and cube roots. The motivating question for us is, can I do the same trick I did before with the quadratic polynomials? Can I somehow say I can find these three roots by using some type of a function w of z? So remember, a lot of this comes from this group of faculty that I was working with, and so we were able to work out all of these formulas quite explicitly. So we said, let's say that you give us a cubic polynomial. Let's now write down this complex number p, this complex number q. Those are just the coefficients. Then I can express the roots x1, x2, and x3 in terms of this nasty looking function w of z, where all I have to do is just evaluate at this number z naught. So it's kind of a lot to take in here on the slide. So let me just kind of point out what are the important aspects. So number one, you give me a degree 3 polynomial. Once you do, number two, I simply compute this number p, that's just a constant. This number q, that's a constant. This number z naught at the bottom, that's a constant. Finally, once I have all of those, I have this weird looking function w of z here, and just evaluate w at this z naught that's at the bottom. Once you have that, here are your three roots. Now, of course, the thing that should be going through your mind is, how did I find this function w of z? We're going to come back to that before the day is over, but this is just to say very explicitly, here you go. Here's the formula for how to find the three roots of a cubic polynomial without having to worry about the formulas that you saw before. Now, what I want to do is ask the question, like last time, if I try to have these loops, how does that correspond to how the three roots move around? So let's try to do the same idea as before. On the right, I'm going to have my z, and there I'm just going to loop around my L of t. I'm just going to loop around however I want. The two red dots correspond to 0 and 1, so I just have a loop around 0, a loop around 1. On the left, I have my three dots, which are the three roots of a cubic. So now let's just have fun and go at it. So again, on the right, we're just looping around my L of t however I want. And now you can see how the roots on the left start to get permuted around, right? It's almost like a weird kind of a juggling thing, right? So as I'm having fun with my loop on the right-hand side, my loops on the left, my paths on the left, they start to kind of permute around. You can really see some weird things are happening. Sometimes the three of them kind of loop around in a certain way. They look like they're in cycles or permutations. Notice as I go through the two red dots, they kind of collapse together, or maybe they even separate apart, right? There's something deeper happening there that I'll try to say a little bit later. But again, we're just looping around on the right merrily. Those correspond to these three paths on the left. So now we have degree 2. We have degree 3. So let's try to have some motivating questions here to kind of see what is really happening. So I just said that we have these functions z of w, and I tried to write down these functions w of z, but what is all of this here, right? I have these notation 2f1, I have these w of z's, I have these z of w, so what is going on? Where is all of this really coming from? Also, I just mentioned that I can express the roots of a quadratic and a cubic somehow using these functions, but can I do the same thing for all polynomials? In particular, what happens for degrees 4 and 5? And then finally, we have this weird kind of permutation of the roots, almost like a juggling pattern. So is this related to this weird idea of Galois theory? Maybe some of you have heard of it. And this is part of a larger phenomenon. So these are going to be our three motivating questions. And if you permit me, I'm going to try to spend the next 15 minutes or so and give you sketches of the answers here. Right? So what is the bigger picture? Right? What is really what's going on? So now I'm going to pull the veil back and I'm going to show you kind of the big picture in complete generality here. All of this really gets a start from a series of theorems back around the mid-1900s or so. Remember I mentioned before that we're trying to focus on these so-called compact connected Riemann surfaces. That's just a fancy way of saying that I have something that's defined by a single polynomial equation, so like some f of xy equals 0. The big question is, what can I say about the coefficients of the polynomial that defines this object? Simply put, if I can choose a defining equation for S where the coefficients are not transcendental numbers, they're what are called algebraic numbers, then there exists some rational function, right, ratio of two polynomials, that has at most three critical values. And it turns out that the converse is true. If there exists a rational function that has at most three critical values, then my surface S can be defined by a polynomial equation whose coefficients are algebraic. So this set of results was basically proved by André Weil and Gennady Belyi. Quintic, who was the friend of André Weil, was really fascinated with these set of theorems, really the fact that Weil spent a lot of time proving this hard theorem, and Belyi kind of proved the converse. The proof was just a couple of pages long, that he decided to take a closer look at these functions. So he called these Belyi pairs, right, the Riemann surface and this map Z of W. And he realized that you can kind of encode a lot of information about these in a certain kind of a bipartite graph. Bipartite graph just means I can color the vertices one of two colors. I'm going to call them black and red, just for the sake of argument today. And because Quintic was in Canada writing all of this in French, he called these descendants. I would say that your mentor here, Simon, probably knows more about this than most people on the planet. So if you do want to ask him any questions about this, he's definitely the right person to chat with. Now, what I want to do, instead of getting into all of these crazy definitions, is just to give you some examples to show you that there's a lot of beautiful symmetry that's at play with these objects. So here on the screen, you're not meant to see any of this in detail, is to say that there are examples of these so-called Belyi maps. In this case, I'm only going to look at the sphere. I'm not going to write anything more complicated today. And then these graphs, these so-called descendants, are supposed to be these beautifully symmetric objects. If you wanted to know where some of these pictures are coming from, remember I mentioned that I work with a group of undergraduates, and we spent a lot of time trying to figure out what's the right way to draw these objects, to get them to be animated, to look all beautiful. One thing that I really have thought a lot about in math talks is how do you really come up with just kind of the right pictures and the right movies to emphasize what's really happening. So I do want to give my undergrads credit for coming up with a lot of these images. So Belyi maps, really Belyi pairs, do have a lot of information. And so what I want to do is try to understand some examples of these. It turns out that there's a website called LMFDB. It stands for L Series of Modular Forms Database, which has examples of Belyi maps. So if you're curious just to learn yourself, to kind of learn more, find more examples, play around with them, I highly recommend to go here to LMFDB. There's lots of examples. I don't think that you can find the site via a Google search. I think that the beta is still hidden. But again, I'll have these slides available for you afterwards. You're more than happy to kind of play around with it and get the link there. I want to mention two important statements, though, about these so-called maps. One is work that was done by Felix Klein back in the late 1800s that said there is some interesting group theory that's happening. Now, if you don't know groups, I would say this slide here probably won't mean a whole lot, but I would say don't really worry about this too much. What this says is that there are interesting groups that one can write down, and these groups all somehow act on the sphere. So here I either have the cyclic group, the dihedral group, or these tetrahedral, octahedral, or icosahedral groups. But specifically, Klein wanted to think of these in terms of Mobius transformations. So he said that you have these fractional linear transformations, let's say like for the dihedral group that says I can take W to 1 over W, or I can maybe take W to a root of unity times W. And so these here somehow give me back these self-similarities of the sphere. More importantly, he actually said that these are the only ones. These are really the only groups that you will have that will form the finite subgroups of automorphisms of the sphere. If any of you have heard the phrase like Fouchian subgroups or Kleinian subgroups, these would be examples of all of those. More importantly, Klein also noted that these examples here of belly maps for the sphere were the ones corresponding to the groups that I just wrote previously. There's this idea of deck transformations or the monodromy group, which I won't try to explain much today, but what I'll simply say is that in some sense, the automorphisms of those descendant fonts correspond exactly to the rigid rotations that I mentioned there on the previous slide. So yes, there's a way you can kind of see things like the tetrahedron and the rotations of the tetrahedron by the belly maps that I have here, or things like the icosahedron and the rotations of the icosahedron, all by the descends and the Mobius transformations that I mentioned on the previous slide. So even Klein understood that these are all going to be highly related, so I really want to focus on these examples. That's where a lot of these are coming from. So let me kind of pause for a moment to say, what I really want to do is go back to the fundamental group and try to ask how what we just wrote down in terms of Klein's work is related to the fundamental group. So Klein realized that if I take my fundamental group, the sphere minus 3 points, remember we talked about that before, that's this weird fundamental group thing, that there will be generated by these loops, a loop around 0, a loop around 1, and a loop around infinity. And so I can think of that group, right, fundamental group, as really being related to these three groups that I just talked about, this D, M, and K, which I'm not going to explain too much. What I simply want to say is, remember before, if I had a loop that corresponded to a path that didn't quite go all of the way, this here generalizes that to say that if I have a loop that will then go to a path, but now that path really should be related to a Mobius transformation, a fractional linear transformation. So I'm going to identify a loop L, not just with a complex number like we did before, but some 2 by 2 matrix, right? Something corresponding to this A, B, C, D. And so this here, much more generally, is what's called the monodromy representation. And I just want to point out, instead of worrying about exactly what I mean by that, the idea is that I want to try to write down this representation by asking about like the inverse of these belly maps, going from Z of W to W of Z. If I can do that, I'll plug in this L of T, that gives me back all the information. The main takeaway from this here is I want to take a loop, I want to plug in to W of Z, and I want to see how that loop goes to a path. That's all I'm trying to do. If I have a loop L of T, I want to see how does that correspond to a path. So the big question is, how do I find these so-called inverses? That's all we want to do. We want to find the inverse to somehow understand what's happening with the monodromy. So there's a question here in the chat window. Is there a general formula for these? There isn't really a general formula for the belly maps. It's actually kind of difficult to compute examples of belly maps. There's really an active area of research trying to find good ways in which to do this. That's part of the reason why I would say go to LMFDB. You can see some examples there. Some of the examples that I'm showing here are kind of cutely curated in that they're supposed to be as simple and as pretty as possible, so all the pictures come out nicely. But much more generally, if you want to find an example of a belly map, that is a hard question, but that is a good question you're asking here. Right. So remember, the question is, if you give me a belly map, how do I find its quote-unquote inverse? There's this beautiful theorem that was worked out by a series of letters from Kummer, Schwartz, and Fuchs. If any of you have studied a little bit about Kummer theory, this is the same Kummer. There is the Schwartz of things like the Schwartz triangle groups or the Schwartzian derivative, same Schwartz. And there's the Fuchs that's related to things like Fuchsian differential equations. So these names are people that all were chatting back in the late 1800s. The statement is, say that you give me a Belly map, and let's say you get lucky, and the derivative you see on the screen is equal to the right-hand side for some complex numbers, lambda, mu, and nu. Let's just say you just get lucky and that happens. There is no reason at all for that to happen, but let's say that you get lucky and it does happen. Then you can find the so-called inverse as a ratio of solutions to the hypergeometric equation. It's totally random that in order for you to actually find the solution, you would have to find ratios of solutions to this differential equation. So what we're going to do is just say, all right, fine, if that's the case, if you find a basis of solutions, remember this is the two-dimensional vector space, so that means I can pick a basis f1 and f2, so then the ratio of two solutions would look like a fractional linear transformation, a Mobius transformation, in terms of this ratio f1 over f2. That's all that's happening. So for what we care about, what Kummer would say is, all right, fine, let's go back to this hypergeometric equation. Its solutions involve the hypergeometric functions. Remember, that's what we said a little bit earlier. And the ratios of those are these so-called Schwartz triangle functions. So I'm going to focus on one of these, namely this S0. Notice that it's a ratio of hypergeometric functions. There is something deeper happening here with complex analysis and things like conformal maps from a complex plane to a triangle, which I won't go over, but if anyone has any questions about it afterwards, we can definitely chat about that. So again, the point is, I should be able to find my desired inverses as one of these three functions here. That's sort of the idea. In fact, with the group of faculty, we just worked through and just did exactly that. So remember, I talked about that list of Belly maps that Klein focused on. So if you just run through the argument of Kummer, Schwartz, and Fuchs, you start with this list that Klein had. You then compute the complex numbers lambda, mu, and nu. There's a deep reason why the lambda, mu, and nu's here are reciprocals of integers. And once you do that, then you find the Schwartz triangle functions, and then there's the inverse on the right. So it's straightforward, right? It's actually kind of amazing that they were able to work this out in the late 1800s, but it's very straightforward. There's a question here, did the motivation for the hypergeometric series come from the Belly map or the differential equation? It really came from the Belly map, but it's kind of hard to explain here. There were a series of letters that Klein had with Schwartz back in the 1800s, where Klein kept saying he had these functions and he wanted to quote unquote find the inverse. So Schwartz actually invented this concept of a Schwartzian derivative to figure out, so he understood that he could compute the Schwartzian derivative. These Belly maps are very nice in that they're saying something about triangles on the sphere. So he knew that this lambda, mu, and nu had to be the case. And so what he wanted to do was try to work backwards to say, okay, fine, if you have this here, the map here is to correspond to like these conformal maps from the plane to the triangles. And so he was able to kind of work backwards by saying, these should be the functions, these triangle functions. And I think later he kind of worked out that these triangle functions should be related to hypergeometric functions. But what I'll say is that really a lot of what you're seeing here came from conversations with Klein and Schwartz, right? So remember, these aren't exactly inverses. Like, if I want to say something like, what's the inverse of w squared? There really isn't one inverse. There's a positive square root of z and a negative square root of z. So we're not trying to find an inverse. You're trying to find something like, if you will, like a right inverse or like a section. We're trying to find something where if I plug it in on the right, then I get back the identity. But there might be more than one function that does that. So that's sort of the idea here. So I'm trying to find a function that kind of acts as like a right inverse. And that's exactly what you're seeing here on the screen. Right. So let's try to finish all of this off to say, what's happening here? So remember, we could do degree 2 by just computing things like the square root of z, We could do degree 3 by looking at this belly map, the z of w you see here on the screen, and then we could find the inverse of this belly map by ratios of hypergeometric functions, or if you will, the Schwarz triangle functions. I'm going to try to say in the last couple of minutes, what happens for degree 4 and degree 5? So first of all, for degree 4, there is a way you can find the roots by computing what's called a resolvent cubic. And I'm not at all going to try to explain where these formulas here are coming from. The simple takeaway is that you can express the roots of any quartic polynomial using only square roots and cube roots. That's all that you need. So I want to know, can I express these roots as the inverse of some belly map? And it turns out that the answer is yes. The formulas are kind of nasty, but they just say the following. Explicitly, here are the 4 roots of any degree 4 polynomial, where I'm going to take my w of z, that's here at the bottom of the screen, that's my Schwarz triangle function, and I'll simply will evaluate it at this z naught. The p and q are the formulas that we had on the previous screen. Now, just for the sake of completeness, there's also what's called the resolvent cubic. You can also find the roots of that resolvent cubic in terms of this w of z. There's a subtlety that I have to make this assumption, 3b squared minus 8ac to be 0. I would say don't worry about that too much. That's just a matter of kind of getting the formulas to be here on the screen, which you can already see is pretty bad. But this is really essentially it. Let me just say that you can do the same trick as before. You can look at those loops on the right and see how they correspond to paths on the left. And so here, there's a few different things that are happening. The 4 black dots on the left are the 4 roots of the cubic. The 3 blue dots are the 3 roots of the resolvent cubic. Right, so if you know a little bit of something about how to find the roots of a degree 4 polynomial, you can kind of see what's happening here. So again, the 4 black dots are for the quartic, and on the left, the 3 blue dots are for the resolvent cubic. On the right, we're just looping around, having fun, just moving around however you want. That's my L of t, and you can see how the roots here on the left move around. This is exactly what the formulas are telling us. This is exactly what monodromy is. As I'm looping around on the right, I can see now how my roots permute around on the left. And let's just do one last slide here. So I want to talk about, finally, what about degree 5? Well, unfortunately, there's a theorem that says we cannot express the roots of degree 5 polynomial using radicals. In fact, one of the big celebrated theorems of what's called Galois theory is that you can only express the roots of a quintic in radicals if and only if its Galois group is a solvable group. I'm not going to worry about what any of that means, but I personally am a little bit interested by this little known theorem by Charles Hermite that came out a few years later that says, well, actually, you can make a transformation so that the roots of a quintic can be expressed in terms of hyperelliptic functions. So the crazy thing is, you cannot express the roots in terms of things like square roots and cube roots and 4th roots like you could for the degree 3, degree 4 polynomials, but you can express the roots in terms of hyperelliptic functions. So I'm going to try to show you on the next screen to kind of wrap everything up. Here's how you can do this. And you can basically reprove this using this modern language of belly maps. So the idea is, let's consider this quintic you see at the very top of the screen. I know it looks weird, but this says here that I want to think of this as a quintic in terms of the variable t, and my z here is any complex number you want. So you fix a complex number, you write down this degree 5 polynomial, and here are the roots that I can express in terms of this w, right? So this ratio of hypergeometric functions. In fact, basically any quintic can be placed in this form as long as you're willing to put these 2 weird conditions here at the bottom of the screen. But this does explicitly say you can write the roots of a degree 5 in terms of this ratio of hypergeometric functions. Now, I'm not going to say for the moment where a lot of these formulas are coming from. Some of this comes from looking at works of like Hermite and Girard and Klein. This is essentially what they kind of worked out, but you can see here explicitly how to do this. And I'll just show you just one last thing just to really kind of hit home. This is why this is really nice. So the final movie I want to show here is what happens as you kind of just play around with the paths going to the loops. So on the right, remember that's my L of t. I'm just dragging around my cursor however I want. The red dots correspond to 0 and infinity. So remember, we're looping around 0, looping around infinity. And on the left, you see the 5 roots. Those are the 5 roots of my Quintic. So you can see here how on the left, everything's being moved around. In fact, if you're curious, this is what Galois theory tells you. Galois theory is just simply going to say that I have so many different ways I can permute the 5 on the left. Monodromy tells you literally the motion. So again, Galois theory would say I have a permutation, but monodromy would say here's how the roots are all actually moving in real time. So if you are interested to maybe learn a little bit more about this, I did have a group of undergraduates some years ago that were working with me. They were really inspired by 3 Blue, 1 Brown. And they wanted to create kind of this cute little stop animation movie where they did talk about what is monodromy, what's kind of happening with the juggling and what have you. So I'll show a QR code in just a moment in case you are curious to learn more. But I hope that I've kind of piqued your interest a little bit in this whole concept of monodromy. You can probably tell that there's really a lot of information that's here, but as my students like to tell me, monodromy is motion. So thanks for your time then. Be happy to take any questions. Yes, I'll be happy to share the slides. There's a good question here. What about higher degrees? So I have to admit, this has been kind of my obsession for many years. I tried to tell a nice self-contained story about what happens with degrees 2, 3, 4, and 5. All of this corresponds very beautifully to belly maps. It also corresponds to things like these Fouchian differential equations, hypergeometric functions, and what have you. This is a very classical way of doing all of this. I would say if Klein were sitting here in this talk, he might be a little bit upset saying this is all kind of obvious and things that he knew back in the 1800s or so. There's a totally different way of doing this, which works for any degree in polynomial, any polynomial you work. You can solve any polynomial by using a generalized hypergeometric function. Here I'm using the hypergeometric function 2f1, but if you're willing to go to something like pfq, then you can kind of set up a very similar argument to express the roots of any polynomial using this generalized hypergeometric function. So yes, you can actually do this much more generally. I just told the story here in such a way that I could just focus on belly maps. So there's another good question here. Can we convert this to other fields of work where it may not work at first, maybe parametric systems or non-Euclidean geometry? So ironically, everything that I said here with belly maps actually does work more generally for non-Euclidean geometry. I only focused on the sphere because, again, I was trying to tell a very, very specific story here. What's happening much more generally is that you want to take a look at what's called the inverse Galois problem. So here, what I didn't quite say is the groups I'm all working with, the monodromy groups themselves, are things like the tetrahedral group, the octahedral group, the icosahedral group. They all are kind of like, A4, S4, A5. That's why at most you have degree 4, degree 5. If you wanted to work much more generally, then you have to work with other Riemann surfaces. And so it turns out that you can try to do this for things like polynomials of degree 7 and what have you. This is actually what Klein did in his own research. He wanted to figure out how do you have the roots of, say, a degree 7 polynomial. But it turns out there that the Riemann surface you have to deal with is very complicated. If any of you have heard of things called the Klein quartic, then you would know the Klein quartic is kind of this object. I believe it has genus 3, so non-Euclidean geometry, but he wanted to try to understand polynomials of degree 7 by looking at the automorphisms of the slightly more general Riemann surface. So simply put, you're totally on the right track. If you really wanted to do this for any polynomial, you have to go beyond the sphere. You have to have genus 1 and higher. I only did genus 0 because the pictures are pretty, but definitely Klein and others would tell you what we're doing here is too limited. In the general sense, you have to go to non-Euclidean geometry. So that is an excellent question. Other questions then? Well, certainly I'm happy to send over a copy of the slides. I did find a few typos that I want to clean up first, but I'll just do that and send that over to you in the next hour or so. Feel free to send me an email if you still do have questions about things. I think that some of you have already done a little bit of work kind of in some of the different aspects of things here, but I really do hope that you all continue working in these areas, because I do find this really to be fascinating myself. There's a couple other questions that just came up. Are we limited to genus G orientable surfaces, or can we go beyond in defining belly maps? That is an excellent question. Usually, one focuses on Riemann surfaces, and by definition, a Riemann surface is an orientable manifold of, I would suppose, dimension 2. You can attempt to make these definitions on a non-orientable manifold. What I mean by that is, remember that kind of a lot of what I'm working with is in projective space, things like, P1 of C and what have you. You can try to go to where your curves live, which will be like P2 of C, but sitting inside of P2 of C, you have P2 of R. And P2 of R is a non-orientable surface. So I believe that you can attempt to draw a descent on a non-orientable surface. I don't quite know what that would look like, but I do believe that it is possible to do some of this argument for surfaces that are not orientable. I'm just not completely sure myself how to do that. There's another question here. Were the explicit forms of these functions discovered before, or were they discovered in your research GRP, my research group? Yes and yes. So these were belly maps that were known by Klein, but I'm kind of lying there a little bit because Klein would have studied these in the late 1800s, whereas belly maps weren't defined until the late 1900s. So what Grothendieck and others would say is, even though we're calling these belly maps now, Klein would have identified all of these maps back 150 years ago. So I would say, yes, they were known 150 years ago, but the modern language wasn't really known until now. So the goal of the research group was to say, here are formulas that probably Klein would have known late 1800s, but we're going to use the modern language of belly maps and sections and hypergeometric functions to kind of redo everything, but more in a modern language. So in some sense, we kind of discovered them, but it's more like we rediscovered them just because we're using the modern language. But again, I would say if Klein were sitting here on this talk right now, he would say, yeah, he definitely knew all this stuff back in the late 1800s. But yeah, definitely that's an excellent question. Yeah. Yes, I still do hold these research groups. As I mentioned, I had a group of faculty that I just worked with last week, so we are still cleaning up some of the formulas here. One of the things I didn't say here is that we really want to show for any degree 4, for any degree 5, there's a couple of weird conditions I had here on the slides to get things to be simple, but for any degree 4, degree 5, we should be able to express all of the roots using these hypergeometric functions. So this is just saying we want to completely redo Hermite's theorem using belly maps. That's kind of one way in which we can motivate the interest in doing belly maps. So that's currently what we're working on this summer. We'll probably finish that off in the next couple of months. I do have undergraduates that I'm also working with on a lot of this. Some of the 3D pictures that you saw, some of the movies that you saw, I'm currently working with a group of students on a lot of these. For example, one thing we're talking about is how to generate some of these three-dimensional objects using a 3D printer. We're still close to getting that done. We're also looking at how to maybe find a way to visualize a descending font using a VR headset. So we don't have our hands on Apple Vision just yet, but that's kind of the idea, is that we should be able to generate some of these objects where you can put on something like a Vision Pro, or even just like take your cell phone and just kind of like, see this image in virtual reality and kind of walk around it in a virtual space. You can really see kind of what the inside looks like, the outside looks like. So I really am working with students on the visualization of a lot of these things now. So yeah, so no, thanks for these great questions. Other questions then. All right, if no other questions, then yeah, thanks very much for your time and attention. Yeah, I really do appreciate it. Being online here is always weird, but you all have definitely had some great questions for conversation today.
Thank you for a great talk. So yeah, let's move on to the next part of class now.